Hi, welcome to the class again, and in this lecture we are going to study geometric transformations, rotations and translations. So you might be wondering why we need to have this lesson on linear algebra. Well, the reason we need to have this lesson on linear algebra is because we want to understand how a camera captures an image of an object in the world and what happens if the camera moves. So that's what we want to understand. So there are two things involved here. So imagine that we have a camera, and in that camera we have a coordinate system. So in the coordinate system of the camera, we are going to have x, y, and z coordinates associated with various points on the object. Right. Now what happens if this object moves? So all these coordinates will change. Coordinates change. Now, is this really fundamental? Suppose I have a chair and I move the chair. Is the chair now a different object? In a certain sense, no, it's the same object. But if I measure the coordinates with respect to the camera, those have changed. So we want to distinguish between these two effects. And we use these two terms in computer vision. One is pose and the other is shape. So pose refers to the relationship of the object to the camera. And it's going to be characterized by how it is situated with respect to the camera. So if I am looking at an object and then I move that object, then the pose changes. But the shape doesn't change. The shape changes only if I break that object or tear it apart or some such thing. Is independent of the relationship of the object to the camera. So let me illustrate this with an example from high school geometry. So suppose I have a triangle and then I can move it. So I can move it to some new place and I can rotate it at the same time. So what's happened is that I have translated it and I have rotated it. But it's the same triangle. So in high school geometry, we call this the notion of congruence. So we'll say that these two triangles are congruent, and there are a number of conditions by which we can figure out whether two triangles are congruent. So we want to develop this idea more generally. And basically what we are going to come to is some notion that there are certain transformations you can do and that does not change the shape. So shape of the triangle remains unchanged under the transformation of rotation and translation. Note, the coordinates x, y of various points on the triangle have changed. So that's the fundamental distinction. Pose changes when we rotate and translate the object. Shape does not. Okay, so that motivates the study of rotations and translations. So let's think about this more generally. So we have rotations, and I'm just trying to rely on your intuition of what rotations are, and translations. And now we will operate like mathematicians. Are these special cases of more general transformations? That's the question. And the answer is yes. And this special class of transformations I call rigid body transformations. And rigid body transformations include rotations and translations as special cases. Sometimes we will use the term isometry as well. Okay, what do I mean by rigid body transformation? So let's think of what we mean by the word rigid body. A rigid body is characterized by the fact that if there are any points on that rigid body, they have the same relationship with respect to each other as the object moves. So if I have, let's say, a cube, so I consider this cube, and then I can take some points on this cube, and if I move this by some rotation and translation, what will happen? What will happen is that the distances between any pair of points will remain unchanged. Right? If you move the object, the distance between, say, these, the distance between these 2 points will remain the same. So this distance stays constant. So we know that this happens for a rotation and a translation. Now let's think of some object when this won't be the case. So now I will try to draw a balloon. Okay, and now what happens to this balloon is that we blow up this balloon. It becomes much bigger. So if I had points A and B, now these points are much further apart, A prime and B prime. So the distance between A prime and B prime is unequal to the distance between A and B. And in this example of the balloon, this is not a rigid body motion. Okay, so we have seen some example, an example of a rigid body motion and an example which is not a rigid body motion. So now let's get into the math of this. And we have defined this formally. So now we have this formal definition. Rigid body motion is a transformation that preserves distances. Okay, so let's state this more precisely. Suppose I have a point A. This is in three-dimensional space, and I have some point B, and this is also in three-dimensional space. Now I apply some transformation, and let's use the notation psi for this transformation, and this gives me the new location of the point psi of A and the new location of the point B, which is psi of B. So how do I measure the distance between A and B? So what is distance between A and B? Well, this is given by the length of the vector corresponding to the difference between the vectors A and B. So this is just a notation for length. So just to remind you, suppose we have a vector V, which has three components, v1, v2, v3. Then the norm of V is given by v1 squared plus v2 squared plus v3 squared, and then you take a square root of this whole thing. So this is the notion of length, which you have studied in high school and in linear algebra classes. So what we do here is we take the difference between the vectors A and B, and then we compute the length of that difference, and that's the distance between A and B. Okay, so now let's use this notation here. So what's the distance here? So the distance is going to be the norm of the difference between A and B. And what's the difference here? It's psi of A is the point A after the transformation, and psi of B is the point B after the transformation. And we take the length of this difference. So if psi is so we can now define this. If psi is a rigid body transformation, then the length of A minus B is equal to the length of psi of A minus psi of B. Okay, so that's my definition. So you can't really argue with this because this is the definition. Okay, so mathematicians always start with some definition inspired by physical considerations. That's what we have done here. We want to allow for the case when an object moves without breaking apart or stretching or some such. We have been inspired by physical considerations to define the notion of rigid body transformation, but now we have got a mathematically precise definition. And what we will do now is to just try to follow through on this definition. So now we'll kind of operate like mathematicians who use the physical world as inspiration for some definitions, but then they try to find examples, prove theorems, and so on and so forth. In our case, these are going to be about rotations and translations, but first I have to prove that rotations and translations are rigid body transformations, and this is what I will try to do next. So let's consider examples. First, is translation a rigid body motion? That's my question. Is it? Well, let's define what is translation. So translation is that you just shift an object by some amount. So if I have a point A, after the transformation it's going to be A plus some shift which I'm indicating by T. Right? So that's the definition of translation. So this is the definition of translation. Okay, can we check that this is a rigid body motion? How do we do this? Okay, so if we have the point A, that's going to get transformed to A plus T. If we have the point B, that's going to get transformed to B plus T. Okay, we have some difference here between the points A and B. So this is the distance, this is the original distance. And now let's figure out the distance between these guys. So the distance between these guys is going to be given by A plus T minus B plus T. Correct? And what is this going to be equal to? This is going to be equal to the distance, because the T's cancel out. So this was the old distance was given. So this is the new distance. So let me indicate here. And the important point is that these two distances are the same. Phew, that's very comforting, and we have convinced ourselves that translation is a rigid body motion. Okay, let's take a break here.